Hello everyone and welcome to your video lesson of physics. In this video I'll be solving the past paper questions of Newtonian mechanics, which is basically the extension of my previous video. Uh, so this is the part 2. Alright, so in today's lesson we have most of the questions from the chapter Elastic Deformation. So let's start with the first one. Number dash 3. A student suspends a spring from a sport. He attaches different loads to the lower end of the spring. For each load attached, he measures the extension of the spring. Figure 3.1 shows the extension load graph obtained. Okay, yeah, so in this one, they have given extension on the y-axis and load is given on the x-axis. And extension is given in centimeters, right? Sometimes load is given on y-axis and extension is given on x-axis, and the graph is uh, pretty much the same. The only difference occurs when you read the limit of proportionality, because after that point the graph has to bend, and in that case the graph would bend towards the extension axis. So in that case it would be bent like towards the x-axis. Had the extension been given at x-axis, like if the extension were given on x-axis and the load were given on y-axis, then in that case your graph would have bent towards the x-axis, right? If when once it reaches the limit of proportionality, right? But so far we have to do nothing with that concept. Let's move on to the question. The extension of the spring is directly proportional to the load. Yeah, we can see from the graph as well. It's a straight line, means they are directly proportional to each other. Say the two features of the graph that show this. All right. So for the features of graph, obviously one thing you can write, the graph is a straight line. All right. Graph is a straight line. All right. And the second one, we can say when the load was zero, the extension was zero. So basically the graph or the line passes through the origin, right? That can be the second feature of the graph. Origin. All right. So these two can be the features of the graph. Now, many of the times I've seen the students would write, first thing they would write, okay, the graph is a straight line. And for the second feature, they might be writing, if the load increases, the extension increases. I mean, this thing is just the same as the first point. Graph is a straight line. So if you write other than that, if you write the second pointer as the load increases, the extension increases, that would not be an independent feature, right? It is just another description for the first one, because uh, if increasing the load, the extension increases, then in that case the graph would be a straight line. So you write that thing, it would not be an independent feature. It is just uh, another way of describing the first pointer. Okay, so that's why you have to write these two features. All right, let's move on to the next one. Describe how the student can show that the spring reaches its limit of proportionality at 8.0 Newton. Okay, so basically they are saying that at this point the graph has reached its limit of proportionality, but how the student can show that? All right, the student can show if he plots the graph further, if he extends the line after collecting the data. for the load more than 8 Newton, and plotting the points, joining the points, getting the graph, getting the curve, and he can then show that. Okay, so let us phrase it. The student needs to add load beyond 8 Newton and find the extension, or just finding that context means you need to measure the extension experimentally from the ruler and find the extension against that load. Plot the points on the graph and it needs to join the points freehand, because in that case it would be a curve. Join the points freehand, and the extension load graph would bend towards extension axis, showing that the spring has reached its limit of proportionality at 8.0. Showing spring has reached limit of proportionality at 8.0 Newton. Because right after that, as he would collect the data and then he would plot the data on the graph, he would find out that as right after the 8 Newton point, the graph is no longer a straight line. It is a curve, and the curve is bending towards the extension axis, which in that case is the y-axis. Because at that point, as soon as it reaches the limit of proportionality, the spring constant now decreases. The spring would become easier to expand, and if it becomes easier to expand, there would be more extension for uh, the same amount of load. For the same increase in load, the extension would now be comparatively greater. So that was the first one from the topic of elastic deformation. All right, this one I'm going to skip for a while, and because right now I want to do the questions related to elastic deformation. Okay, let's start with this one. Number dash 6. Figure 2.1 shows a weight of 4.0 Newton attached to a spring. Then you can see that in the figure 2.1 as well. The unstretched length of the spring is 8 centimeter with the weight of 4 Newton attached to the spring. The length is 14.0 centimeter. the spring is within its limit of proportionality. All right, so we can apply the Hooke's law. State what is meant by the limit of proportionality of a spring. All right, the first one has to do nothing with this above mentioned statement. It is just facts based question, information, data, and information based question. Limit of proportionality. So it is a point beyond which extension of a spring. All right, we gotta be more specific because they are asking about the limit of proportionality of a spring. So you have to include that in your statement. Uh, which extension beyond which extension of a spring is no longer is no longer proportional to the load. All right, so you can phrase it in a different way as well, but make sure you're writing the key terms. It should not be like in must include the key terms. It should not be very elementary. All right, moving on to the part B. The 4.0 weight is now replaced with 2 Newton weight. Calculate the new length of the spring. Okay. Now, one thing, very famous question, very famous pointer that they test you about, uh, in which basically you need to apply the Hooke's law, which says force, deforming force equals to K times the extension. K is a constant, so that means F over X equals constant, right? The ratio of deforming force, or the ratio of, in that case, you can just call it force, and the extension is always constant. So if that is constant, I can write it as F1 over X1 equals F2 over X2. F1 represents the load that you have added at that particular moment, and X1 represents the extension when that load was there. F2 represents the new load, and X2 represents the extension in consequence of that new load. All right, so even if you don't nothing about it, the concept is not there, but you have to be aware of the formula, okay, which is F1 over X1 equals F2 over X2. This is an important formula, and then you can do it mathematically as well. I'll show you how you can do it mathematically, which is just another way of the same formula. You're actually using the same formula, but apparently it looks like that's another way. All right, what is the previous force that we had? It was 4 Newton. And X1, I told you X1 stands for extension. Okay, it stands for extension on that force, right? So you have to be careful with it. It's not the total length, it's not the original length of the spring, it's the extension. Okay, now what is the extension of the spring when the weight was 4 Newton? Okay, let's check it out. Here you have some information. The original length of the spring was 8 centimeter. Okay, unstretched length means the original length of the spring was 8 centimeter, and when you added the weight of 4 Newton, the new length is now 14 centimeter. All right, so it looks something like this. So you had a spring, and the length of that spring was 8 centimeter. Okay, Let's write 8 centimeter over here. All right. Now, once you added some load on that, the spring extended a bit. Let's make it slightly shorter. All right. So once you added a weight of 4 Newton, the total length of the spring is now 14 centimeter. Now the question would be how much the spring has extended. So originally it was 8 centimeter. As you added the load of 4 Newton, it has now extended to 14 centimeter. How much is the extension? Simply you subtract these two. All right, and that would be 6 centimeter. All right, so you might have studied in that way that we have a formula that reads the new length or extension equals new length minus the original length. All right, if you want to like refer to that formula, you just straight away use that formula. You get the extension in any case would be 6 centimeter. So I'll be writing 6 centimeter over here equals what is the new what is the new force now? The 4 Newton weight was replaced by 2 Newton. Okay, so let's write 2 over here. And what would be the extension against that force? It would be x that we need to calculate. So let us now sort it out, cross multiply this one. It would be 4x goes to 12, and then you can write x equals 3 centimeter. All right, so what does that represent? X2. Okay, let's write x2 here. 4 times x2. Now what is that x2 representing? It is representing the extension in the spring when the weight was 2 Newton. But they have not asked you to find the extension. Rather, the question is calculate the new length of the spring. All right, so the new length of the spring, that would be the original length plus the extension against that force, which we have just calculated. The original length of the spring was like, how much was that? 8 centimeter. Okay, 8 centimeter plus 3. All right, so what do you get? You get 11 centimeter. All right, so let's move on to the next part. Describe how the apparatus in figure 2.1 is used to obtain the reading to plot the extension load graph. So it's pretty much the same question as of this one, the previous one. So you need to obtain the readings of weight or the reading of load, and you need to obtain the reading of extension against that load. And once you have 2 or 3 points, then you can plot it on the graph, join the points with the help of a straight line, or I mean if it has not reached the limit of proportionality, it would be a straight line. So you just simply join the points and you'll get a graph that would represent extension load, right? So let's write it down here. And once again, you have to use the key terms. That's the most important thing. The answer should not be very much general. It has to be specific. You have to use key terms once again. So you have the apparatus, yeah, figure 2.1. load is added on the spring and extension against that load is obtained, and then you can write uh, the way that you would obtain the extension, which is subtracting the original length from the new length. So basically, I'm uh, describing this one formula. All right, in that quotation mark, I've been describing this formula: L n minus L naught. Extension equals to the new length minus the original length. Add more load, or more load is added, and find extension against that load as well. To obtain the readings, or to obtain the points that will be then plotted on the extension load graph, and then you join them with the line. All right, so you don't have to like describe the way you would plot the those points and the way you'll join those points, because the question was merely how would you obtain those readings to plot the extension load graph. They're not asking you about how would you plot the extension load graph. It's just about how would you obtain the readings, right? So you obtain the readings, you add more load in that. All right, so from the rule you'll find out what is the new length of the spring, and then you subtract the new length of the spring, and you take the difference of new length of the spring and the original length, you get the extension. That gives you 1 point. Let's say 8 and the extension was 6, that gives you 1 point. And against the load of, let's say, 10 newton, the extension was 8, that gives you the next point. So that's how you would obtain the points. All right, let's move on to the next one. That says question number 7. Figure 1.1 shows the length of a spring varies as the force applied on it increases. Okay, now this one, you see the question in this one, they ask you about the features of the graph. First of all, you say the graph is a straight line and the graph has x-intercept, right? It does not pass through the origin, rather it cuts the x-axis at like 11 centimeter. So it has x-intercept. Had it been cutting the y-axis like this, you would be writing it has y-intercept. So that would be the other feature of the graph. Anyway, let's move on to the first part. A, determine the length of the unstretched spring. So unstretched spring means they're referring to the point when there was no force acting on the load, right? You did not add any force on the load. You did not add any weight on the load. So at the point when the force was 0, what is the extension of the spring? I zoom it in, and you'll be able to say that the extension of the spring over here is 11 centimeter. Okay, because this one represents 11, then 12, then 13, then 14, and then 15. So 11 centimeter is the original length of the spring, because at that point there was no force added on the spring. So the length was 11 centimeter. All right. Then we have the part B, explain how the graph shows that the limit of proportionality is not reached. Obviously, had it reached the limit of proportionality, the graph would be like bent either towards x-axis or y-axis, and in that case it would have been bent towards the x-axis, because every time the spring reaches the limit of proportionality it bent towards the extension axis, all right, or the axis to where the length is given, not towards the force axis. So in the previous question, if you remember, they had given us the extension on y-axis, and in that case the graph would have bent towards the y-axis. So how does it show that it has not reached the limit of proportionality? A straight line. If you want to add something, you can. Otherwise, that would be enough. The graph is a straight line. If you want to add like some extra stuff, you can say if the spring reaches the limit of proportionality, the graph bend towards the extension axis. But in that case, there's no bend in the graph, so no concept of limit of proportionality so far. All right, let's move on to the next one. A spring is attached to a mass of 0.20 kilograms and placed on a frictionless surface as shown in figure 1.2. Okay, then you can see it on the figure 1.2 as well. The apparatus is placed on the floor of a car. When the car accelerates uniformly in the direction shown, the spring extends. State what is meant by uniform acceleration. Okay. Okay, for uniform acceleration, you have to consider it. Let's say an object started to move when, when let's say the time was 0 second, the speed of or the velocity of the object was 10 meter per second. When the time was 1 second, the velocity was 20 meter per second. When the time was 2 seconds, the velocity was 30 meter per second. When the time was 3 seconds, the velocity was 40 meter per second. And when the time was 4 seconds, when the 4 seconds have passed, the speed or velocity, let's say, was 50 meter per second. All right, and if this one point should not be confusing, because uh, t equals 0 represents the instant when you started to observe that vehicle or to observe that automobile. And once you started to observe that automobile, it was already moving with a speed of 10 meter per second. Okay, this is what I mean here. Otherwise, if you like want to be very basic with it, you can start when time was 0, the velocity was 0. When time was 1 second, the velocity was 10 meter per second, or stuff like that. But so this is the time axis, okay, in seconds, and above that I'm representing speed in meter per second. Now, what is the thing that you're noticing here? What you notice is after every second, there's a change in velocity or there's a change in speed. Once again, here speed and velocity means the same thing. We're not discussing about the direction. In terms of magnitude, it is just the same. So after every second passes, there's a change in speed, and the change in speed is 10 meter per second. Okay, the speed changes by 10 units. Now after the next second, there's once again a change in speed or change in velocity, and the change is again plus 10 meter per second. Uh, in the next second, there's once again change in the velocity, which is just the same. So what you see is the change in uh, velocity, or the change in speed, is equal with respect to the change in time. All right, or I can say the rate of change of speed is constant, because the speed changes 10 meter per second after every second. So this is how we define the uniform acceleration. Now you have to phrase it. Speed or velocity, once again in that case, means the same thing. Velocity of the object increases at a constant rate. All right, and when I say it increases at a constant rate, you don't have to then add with respect to time, because whenever you say at constant rate, that itself means with respect to time, right? So if you write with respect to time, another time, it would be like you'll be writing the same stuff once again, so that may not be acceptable. So you have to write speed of the object increases at a constant rate, or you can, the alternate definition could be equal change in velocity in equal time intervals. Right, so you have to write one of these, and that would be acceptable. Let's move on to the next part. The extension of the spring is 9.0 centimeter using the figure 1.1. Determine, part 1 says the horizontal force on M. All right, this is the first thing that we need to calculate, the horizontal force M. So force needs to be calculated. Let's see what information is given. Yeah, and secondly, it clearly mentions you have to use the figure 1.1. Okay, you have to use the figure 1.1 in order to find the value of force when the extension is 9.0 centimeter. So let's go to the figure 1.1. Here we have, yeah, when the extension is 9 centimeter. Okay, so you have to find the force when the extension is 9 centimeter. All right, so what does x-axis represent here? X-axis is not representing the extension. First of all, that thing should be clear. X-axis is not representing the extension. Rather, x-axis is representing the new length or the total length of the spring. So it is representing the total length of the spring, not the extension, not x, and it's not representing the original length either. So what I can do is I can find out from the graph what would be the new length of the spring, or what would be the length of the spring when it extends to 9 centimeter. Okay, so let's find it out. What would be the length of the spring when it extends to 9 centimeter? And what I know is the original length of the spring was 11 centimeter. Yeah, I already told you, like, we get from the point here that the original length of the spring has to be 11 centimeter, because this is the point where no force was being applied on the spring. So that point corresponds to the original length of the spring. So when there's the extension of 9 centimeter, the new length of the spring, or the overall length of the spring, would be original length plus the extension, which in that case would be 11 plus 9, and that means 20 centimeter. All right, so that was the catch here. Many of the stores, they would go straight away and they would try to locate the point where the length is 9 centimeter. No, it's not the length that is given as 9 centimeter, it is the extension. And you don't have the information about the extension directly from the x-axis of the graph. You have to, like, indirectly obtain the value of the uh, length of the spring by using the extension that is given in the question. So the length of the spring at that point is 20 centimeter. So let's go all the way up till at this point, and this is a point where the length of the spring is 20 centimeter. Now what is the value of force against that length? So from 0.5 till 1.0, right, the total length is divided into 1, 2, 3, 4, 5, 6, 7, 8, yeah, into 10 segments. So each segment, like if you go 1 point before that, it would represent 1.8. Then this one would be, no, so you see there's another way. From 0.5 till 1 Newton, you have a difference of zero point 0.5, and that difference is being divided by 10 lines. All right, so what does one line represent? You divide these two and you'll find out that one line represent 0.05. All right, this is what one line in that case represent. So this one would be 0.6. After two lines you'll be getting 0.6. Then this one would be, and likewise the next, after next two lines you get 0.7. After next two lines you get 0.8. Next two lines you get 0.9. After next two lines you get 1.0. Right, basically you get a difference of 0.1 after every two lines. So in that case this one would be 0.9 and 0.8. All right, so this point here on the y-axis represents 0.8 Newton. Right, so all we had to do was to refer to the figure 1.1, and against the extension of 9 centimeter we calculated that the new length of the spring would be 20 centimeter, and against the new length of 20 centimeter, the force has to be 0.8 Newton. Point 1 after every two lines. I'm just writing all the comments over here because then I upload the solved paper, the solved worksheet on the Google Drive. The link would be in the description. You can uh, hit the link and download it from there. So the force was 0.8 Newton. So this one has this one question might be a little bit tricky for the students because there are one or two things that you need to really consider before you come up with the answer. All right, then in the part 2, the acceleration of m needs to be calculated. All right, so for acceleration we have different ways we can find the acceleration. One of the formula is rate of change of velocity, and the other one being f equals ma, and from there we get a equals to f over m. And then there's another way. If you're given with a graphical method, if you're given with the speed time graph, velocity time graph, then in order to find the acceleration, you find the gradient of that graph. It gives you the acceleration. If you're given with a curve, then the same method, you have to find the gradient of that graph at a certain point by drawing a tangent. Then you find the gradient of the graph at that specific point by drawing a tangent, and that gives you the acceleration of the object at that specific amount of time, at that specific instant of time. So there are like different ways you can find the acceleration. So f a equals f over m, which is the compatible in this case because we're given with the value of force and we're given with the value of mass as well. Force being 0.8 and mass was given as, yeah, it was given in the starting sentences, 0.20 kilograms. So you can write it over here. 0.8 divided by 0.20, and then you simply hit it on the calculator. 0.8 divided by 0.20 gives 4. You can write 4.0 in two significant figures. Yeah, 4.0, and the unit has to be meters per second squared. And just make sure everything is in the standard unit, especially for mass. Was the mass given in kilograms? Yes, it was. So that would be the answer for acceleration.